Now we're going to look at the other extreme, which is completely elastic collisions. Completely elastic collisions. This type of collisions are collisions where the kinetic energy is conserved in addition to momentum. So for this kinds of collisions, kinetic energy is conserved in addition to momentum. Now suppose, let's say you're dropping a ball on the ground. So usually what's going to happen is when you drop it, when it bounces back, it's not going to rise, it's going to go back to the same height because some energy will be lost during the collision. Okay, so it's not going to bounce back to the same height because some of the motion energy will be lost during the collision, maybe to heat energy. But let's say you have a very hard ball and a very hard surface. It's possible that the ball can rise back to the same height because the object didn't lose kinetic energy during the collision. It's such collisions that we call completely elastic collision. Okay, so for this kind of collisions we have two equations, one from conservation of momentum and one from conservation of kinetic energy. Okay, so from conservation of momentum we're going to look at one-dimensional problem. Conservation of momentum, we have the following equation: m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. But in addition to momentum, kinetic energy is conserved. Okay, so we're going to have another equation from conservation of kinetic energy. Okay, that is the sum of the kinetic energies of the two objects before collision equals the sum of the kinetic energies of the two objects after collision. And as you remember, kinetic energy is half times mass times speed squared, right? So that becomes, we have the kinetic energy of the first object before collision, kinetic energy of the second object before the collision. So this gives us the kinetic energy of the system before collision, and then we have the kinetic energy of the first object after collision, and then we have half m2 v2f squared, which is kinetic energy of the second object after collision. Okay, so the kinetic energy before collision equals kinetic energy after the collision. All right, now let me give this equation names, 1 and this one 2. So I'm going to simplify these equations because you see this equation is cumbersome, it involves squares, so we have to simplify it. Our goal is to come up with an easier equation by combining these two equations. Okay, so I'm going to start by combining m1 terms on one side and m2 terms on both sides. M1 term on one side and m2 term on the other side. Okay, so this becomes m1 v1i minus v1f. So 1 implies, if I took the m1 terms to one side, I'm going to take the other side, so it becomes m1 v1i minus v1f, m1 v1a minus v1f. Okay, and then I take this to the other side, I've got m2 v2f minus v2i. Okay, this equals m2 v2f minus v2i. Okay, so let's call this equation 3, let's say, and then we're going to do the same thing to equation 2. We're going to put the m1 terms on one side and the m2 terms on one side. Okay, so equation 2 implies, if you put the m1 term on one side, First of all, you can see that we can cancel the half from the whole equation. Okay, so we don't have to carry it. So we have m1 v1i squared, okay, and then we take this m1 term to the other side. We get minus v1f squared. Minus v1f squared equals, and then we put the empty terms on one side. You see we've got v2f squared over here, v2f squared, and then we take this one to the other side. We get minus v2i squared. v2i squared, okay? So let's simplify this. This is the difference between two squares. And if you remember, the difference between two squares is equal to the product of sum and difference, right? So factorization gives us m1 v1i minus b1f b1i plus b1f equals m2, the same thing over here, b2f minus b2i, and then b2f plus b2i, okay? Let's call this equation 4. Equation 4, okay? Now we're going to divide equation 4 by equation 3, okay? So dividing equation 4 by equation 3, okay? So this is equation 4. We have m1 b1i minus b1f b1i plus b1f equals m2 v2f minus v2i, and then we got v2f plus v2i, okay? Now since these two are equal, I'm going to divide this side by this one and this side by this one, okay? So we have the following. We've got m1 b1i minus b1f, and then I divide this by the right side, which is m2 v2f minus v2i, okay? Now you see we have a lot of simplification. m1 goes with m1, and then this term goes with this term. So on this term, on this side, we just have v1i plus b1f, okay? And on this side, m2 goes with m2, v2f minus 2i goes with this one. We just get this one, v2f plus v2i, okay? Again, let's make it symmetric. Let's put the I terms on one side and the f terms on the other side. That gives us v1i minus v2i equals v2f minus v1f, okay? Again, let's make it symmetric. We start with 1 over here. We're going to start with 1 on this side. So it will be the negative of v1f minus v2i, okay? So we have, maybe we'll write the other side. We have v1i minus v2i equals the negative of v1f minus v2f, okay? So you see we got a much easier equation to use by combining those two equations, all right? Now instead of using the conservation of momentum equation and conservation of kinetic energy equations, we can use the conservation of momentum and this equation to solve problems, okay? So let me say equations of a completely elastic collision. Completely elastic equation, okay? So the first one is the conservation of momentum. We got m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, and instead of the conservation of kinetic energy, we're going to use this equation. And the second equation would be v1i minus v2i equals the negative of v1f minus v2f, okay? So for a completely elastic collision, we have these two equations available to us, which means we can solve for two variables, okay? So for this kind of collision, if you know the velocities before the collision, you can actually calculate the velocities after collision, okay? So let's look at an example. Let's say maybe a 2 kilogram object, let's say collides. Let's give the speed first. A 2 kilogram object moving to the right, let's say with a speed of maybe 5 meters per second, collides with a 1 kilogram object moving with a speed, let's say, of 2 meters per second in the same direction. Now the question is, if the collision is completely elastic, calculate their speeds after collision. Okay, so this collision is completely elastic, which means we can use these equations over here. All right, let's write the given values. Let's call the 2 kilogram object M1. So we've got M1 is 2 kilograms. And its initial speed is 5 meters per second. Okay, so we've got V1I equals 5 meters per second. The second object has a mass of 1 kilogram. So let's say M2 is 1 kilogram. Okay, and speed is 2 meters per second, the same direction, so they're both positive. So V2I is 2 meters per second. All right, now the question is to calculate their speeds after the collision, question mark, and V2F, question mark. Okay, so we have two unknowns, but we have also two equations, so we should be able to solve it. Okay, so I'm going to start from the equation of conservation of momentum, which is M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Okay, let's plug the numbers. M2 is 2, V1I is 5, plus M2, that's 1, V2I is 2, equals M1, 2, we don't know V1F, and M2 is 1, and we don't know V2F. Okay, so we've got 10 plus 2, 12. So we've got 2 V1F plus V2F equals 12. Okay, so I've got this equation in two variables, but I'm getting another equation to solve the problem because I can solve for two variables from one equation. All right. Okay, and then I'm going to use the second equation for completely elastic collisions, which is V1I minus V2I equals the negative of V1F minus V2F. Okay, so we've got V1I minus V2I equals the negative of V1F minus V2F. Okay, so V1I is 5, V2I is 2, equals the negative of, we don't know V1F, we don't know V2F. Okay, so this is 3, but we have a negative over here, so that gives us V1F minus V2F is negative 3. Okay, so we have two equations available to us. Now there are two ways of solving a system of linear equations like this. We can use either the method of elimination or method of substitution, whichever you feel comfortable with. But probably in this case, substitution might be easier. So what I'm going to do is I'm going to use this equation to separate V1F. That'll give you negative 3 plus V2F. Okay, and then I'll replace v1f with this expression to get an equation in one variable. Okay, so if I put this instead of v1f in this equation, I get 2 times -3 plus b2f plus v2f equals 12. Okay, I just replaced this one over here by this expression. So if I expand, I get -6 plus 2 v2f plus v2f equals 12. Okay, so we take the other side, becomes 18, and this becomes 3 v2f. Okay, so we've got -6 plus 3f equals 12. I mean v2f. So we have 3 v2f equals 18. Okay, it follows that v2f is 6 meters per second. So this is the speed of the 1 kilogram object after collision. And then we can go back to this equation, v1f equals -3 plus v2f. Okay, v1f equals -3 plus v2f. Okay, but we know v2f is 6, so we got -3 plus 6 equals 3 meters per second. Okay, so the speed of the first object after collision is 3 meters per second, and the speed of the second object after collision is 6 meters per second. Now we're going to look at two-dimensional collisions, that is, collisions in a plane. So far we've been dealing with one-dimensional collisions in a straight line, but now we're going to look collisions in a plane. We're going to have both x and y components. Okay, so let's look at two-dimensional collisions. Two-dimensional collisions. So in this case, we have to use vectors. Okay, so the equation for conservation of momentum in two dimensions, we have already stated it, but let me write it again, would be m1 b1i vector plus m2 b2i vector equals m1 v1f vector plus m2 v2f vector. So we have to use this equation to solve two-dimensional problems. Now you can express the vectors in the IJ notation, and you can use this equation, but also we can simplify this to two algebraic equations. Thus we can write this in component form. If two vectors are equal, then obviously their components are equal, right? So in component form, we have the following two equations. Okay, if two vectors are equal, their x components are equal, right? So you've got e1 v1ix plus m2 v2ix equals m1 v1fx plus m2 v2fx. Okay, and also the y component should be equal. So you've got m1 v1iy plus m2 v2iy equals m1 v1fy plus m2 v2fy. Okay, so either you can use this vector equation and use the IJ notation for the vectors, or we can decompose into algebraic equations. Okay, so this is the component form of the equations for two-dimensional collisions, and this is the vector equation we have to use. All right, so let's consider an example. Suppose we have the following situation. Let's say this object is, let's say m1 equals 10 kilogram, and then let's say initially it's going this way, maybe with a speed of 10 meters per second. Okay, and then we have another object going north, let's say it's m2 equals maybe 4 kilograms, okay? It's going in this direction, let's say with speed of 8 meters per second, and then let's say they collide here. And then suppose we know this object over here goes this way. This is the 10 kilogram object. This is M1. Okay, this is after the collision. Let's say this angle is 7 degrees, and suppose we know the velocity is also, let's say, 6 meters per second. Okay, so the problem is you've got a 10 kilogram object moving to the right with a speed of 10 meters per second, collide this with a 4 kilogram object going north with a speed of 8 meters per second. Now after the collision, this object over here goes with a speed of 6 meters per second at an angle of 37 degrees. Now the question is, we want to know what happens to this object after the collision. Okay, which way does it go and with what speed? Alright, so let's write the given values. You've got M1 is 10 kilograms. Okay, now we know the magnitude of the velocity is 10 meters per second. Okay, and the direction is east, so T1 is 0. Okay, so this implies V1ix is the speed 10 times cosine of 0, which is 10, and then the y component is 10 times the sine of 0, which is 0. Okay, so these are the components we need. And then what else do we know? We know also the final velocity of the first object. So what we know is the magnitude of the velocity of object 1 after the collision is 6. Okay, its direction is 37. Theta 1f is 37 degrees. Okay, so this tells us b1fx is the magnitude of the speed times cosine of 37. Okay, cosine of 37 is 0.8, so you get 4.8 meters per second. Okay, how about b1fy? b1fy would be 6 times the sine of 37, and sine of 37 is 0.6, so it's going to be 3.6 meters per second. Okay, what else do you know? We know the information of the second object before the collision. Okay, so we have v2i, its speed is 8, its direction is north, which means 90 degree. Okay, it's 90 degree. So v2ix is its magnitude 8 times cosine of 90, that's 0, and then v2iy is 8 times sine of 90, sine 90 is 1, so we have 8. Okay, the question is find out what happens to this object after the collision. Okay, so we're trying to find this one, v2fx question mark v2fy question mark. Okay, all right, so we can calculate v2 of x from the equation for the x components. So let's write that equation. That is m1 v1ix plus m2 v2ix equals m1 v1fx plus m2 v2fx. Okay, let's plug the numbers now. m1 is 10. Okay, the x component of the velocity is 10, speed over here, times 10, plus m2. m2 is I think it's 4 kilogram object, so let's put over here m2 is 4 kilogram. All right, so m2 is 4, and its x component, the x component initial velocity is 0 equals m1 10 v1fx. You see, we've already calculated over here, so over here is 4.8, So we've got times 4.8 plus m2, 4. We don't know the x components of the velocity of the second object. All right. So we've got 100, 0. This is 100. Equals, this is 4.8 times 10, 48, plus 4 v2fx. Okay. So we've got 4 v2fx equals 100 minus 48, which is 52. So v2fx is 52 divided by 4, okay, which is 13. Okay, that's its x component. Now to find its y component, we're going to use the y equation. Okay, and that is m1 v1 iy plus m2 v2 iy equals m1 v1 fy plus m2 v2 fy. Okay, so let's plug in the numbers. m1 is 10 and v1i is 0 because it was going horizontally. You see, it's 0. So times 0 plus m2 4 v2 iy, this is going north, so it's just going to be 8. All right, times 8 equals m1 10 v1 fy. You see this one over here, 3.6. So this is 3.6, and then we got plus 4, and then we don't know v2 fy. Okay, so this is 0. This is 4 times 8, 32. So 32 equals, that is 36 plus 4 v2 fy. Okay, so you've got 4 v2 fy equals negative 4. So v2 fy is negative 1 meters per second. Okay, so you see, this object after collision moves with a velocity of 13 meters per second by this way and 1 this way. So we'll go somewhere like this. All right, so these are the x components of the x and y components of the second object after collision. Okay, now let's do the magnitude direction. The magnitude v2f, let's do magnitude, would be square root of v2fx squared plus v2fy squared. Okay, that is square root of 13 squared plus negative 1 squared, still approximately 13. Okay, and then the direction theta to f is tan inverse of v2fy divided by v2fx. Okay, that is tan inverse of v2 of y is negative 1, and this one is 13. Okay, so it'll be the direction of the velocity. All right. Now the next section, we're going to look at center of mass. Center of mass. First, we're going to look at center of mass of system particles, and then later we'll look at center of mass of a solid system of particles. Okay, the center of mass is the weighted average of the position vectors of the particles weighted by their masses. This is the weighted average of the position vectors of the particles course, weighted by their masses. Weighted by their masses. Okay, so the contribution, the average, depends on the mass of the particles. The greater the mass, the greater the contribution to the average. This is also what they call the center of gravity. Now, you can balance an object at center of gravity if you want to, if you want to look at it that way. All right. So what does weighted average means by their masses? Well, you add the position vectors and then multiply them by their masses. Okay, so this is position vector of particle 1, m2 times position vector of particle 2, m3 times position vector of particle 3, and so on. And then you divide by the total mass. Okay, that is m1 plus m2 plus m3, and so on. So this is the definition of center of mass. Okay, the average of the position vectors weighted by their masses. Okay, now you can express the vectors in the IJ notation, and so you can get an expression for the IJ notation of the center of mass, or you can separate this into two x, into the x of center of mass and y of center of mass. Okay, so with RCM equals XCM and YCM, these are the components of the position vector center of mass. Okay, so if you take the x component this of the left side, that should be equal to the x component of the right side. So this will be x1, y1, x1, x2, x3, and so on. So we get the x component of the center of mass is m1, x1 plus m2, x2, and so on, divided by m1 plus m2, and so on. Okay, and the same thing for the y. It is m1, y1 plus m2, y2, and so on, divided by the sum of the masses, and so on. Okay, so this is the component form of the center of mass. Okay, now let's look at an example. Let's say particles of masses, let's say maybe 1 kilogram, 2 kilogram, and 3 kilogram are located at, let's say, maybe 3-4 meters, maybe -2, 5 meters, and maybe 3, -7 meters. Okay, the question is, determine the location of their center of mass. Determine the location of their center of mass. Okay, so what do we have? We have m1 is 1 kilogram, and this is its coordinate. Okay, that's x1, y1 is 3-4. Okay, and then we have m2 equals 2 kilogram, meters, and its location x2, y2 is -2, 5 meters, and then you've got m3 equals 3 kilograms, and then its location x3, y3 is 3, -7 meters. Okay, so we have to find the location of the center of mass. So let's calculate x1, the x component of its center of mass. So we've got xcm equals m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Okay, so let's just plug the numbers. m1 is 1 and its x coordinate is 3. Okay, m2 is 2 and its x coordinate is -2. So you've got 2 times -2, and then m3 is 3 and its x coordinate is 3. So you've got plus 3 times 3. And then we divide by the sum of the masses, which is 1 plus 2 plus 3. Okay? So we have 3 minus 4, -1, -1 plus 9, 8. And then 1 plus 3, 6. So that is 4 over 3 meters. So this is the x coordinate of the center of mass. We'll do the same thing for the y. ycm equals m1 y1 plus m2 y2 plus m3 y3 divided by the sum of the masses, which is 1 plus 2 plus 3. Okay, let's plug the numbers. m1 has a mass of 1 and its y coordinate is 4 plus m2 has a mass of 2 and its y coordinate is 5. m3 has a mass of 3 and its y coordinate is -7, and then we divide by the sum of the masses, 1 plus 2 plus 3. Okay, so you've got 4 plus 10, 14, 14 minus 21, -7. So this equals -7 over 6 meters. Okay, therefore the center of mass xcm ycm is 4 over 3 and then -7 over 6 meters. Now let's look at the velocity. Velocity of the center of mass of a system of particles. Okay, so we want to find out, we want to get an expression for the velocity of the center of mass. Okay, so remember, velocity is the derivative of the position vector with respect to time. So it follows that the velocity of the center of mass is the derivative of the position vector with center of mass with respect to time. Okay, so it follows that VCM is simply the derivative of this one, m1 r1 plus m2 r2 and so on, divided by m1 plus m2 and so on. Okay, so this is m1 derivative of r1 with respect to time plus m2 derivative of r2 with respect to time and so on, divided by the sum of the masses. But you see, this is the velocity of particle 1, this is the velocity of particle 2 and so on. Okay, so we have the following formula for the velocity of the center of mass is m1 times the velocity of particle 1 plus m2 times the velocity of particle 2 and so on, divided by the masses. Okay, Again, you can separate this into the x component and y component if you want. The x component will be called the x component of this equation, and the y component will be called the y component of this equation. Okay, it's the same thing for the acceleration. Acceleration of the center of mass of a system of particles. System of particles. Again, remember, acceleration is the derivative of velocity with respect to time. Okay, so the acceleration of the center of mass is simply the derivative of the velocity of center of mass. Okay, that is the derivative of m1 v1 plus m2 v2 and so on, divided by the mass, the sum of the masses, right? And that is m1 times the derivative of velocity of particle 1 plus m2 derivative of the velocity of particle 2 and so on, divided by the sum of the masses. Okay, but this is the acceleration of particle 1, this is the acceleration of particle 2 and so on. So we have the following formula. So the acceleration of the center of mass is simply a weighted average of the accelerations of the particles weighted by their masses. Okay, so this is m1 a1 plus m2 a2 and so on, divided by the sum of the masses. Okay, example, let's say the center of mass of a system of two particles is moving with a velocity of, let's say, maybe 2 in the I direction minus 4 in the j direction meters per second. Okay, if the velocity of one of the particles is, let's say, -3 in the I plus 6 in the j meters per second, determine the velocity of the second particle, the velocity of the second particle. Okay, so what we have is, we need the masses. So the masses of particles 1 and 2 are respectively 2 and 4 kilograms. Okay, so what we have is, we have the center of mass, BCM, that is 2 in the I minus 4 in the j meters per second, and the mass of the first object is 2 kilograms, and its velocity we're told is -3 in the I plus 6 in the J. Okay, the second particle, its mass is 4 kilograms. We want to find its velocity. Okay, so we're going to use the formula for center of mass, which is VCM equals M1 V1 plus M2 V2 divided by M1 plus M2. Okay, so the velocity of the center of mass is 2 in the I minus 4 in the J. So we've got 2 in the I minus 4 in the J equals, and then M1 is 2, V1 is -3 in the I plus 3 in the J, negative plus 6 in the J. Okay, and then the mass of M2 is 4, but we don't know its velocity. All right, and then this is 2 plus 4. All right, so let's cross multiply. 6 times this equals this, right? So 6 times this is going to be 12 in the I minus 24 in the J equals, let's multiply this by 2, you've got -6 in the I, and then 2 times 6 plus 12 in the J plus 4 times V2. Okay, so let's take this to the other side. We've got 12I, that's plus 6I, that's 18 in the I. You've got -4 in the J, you've got 12 in here. So when you take the other side, it's going to be -36 in the J equals 4 times the velocity of the second particle. Okay, so V2 is 18 in the I direction minus 6 in the J direction divided by 4. Okay, so V2 is, this is 9 over 2, and then this is 9. So this is the velocity of the second particle. All right. Now let's look at center of mass of solid objects. So far we've been looking at center of mass of particles. Now let's look at center of mass of solids. Center of mass of solids. Okay, so let's say we have this object over here. Okay, to use the formula for particles, what we can do is we can divide this into 4 particles. Okay, and then we'll just use the same formula we used it before. Okay, and we have position vector for each of these particles, we multiply by their masses and so on. Okay, so let's say the mass of this ones are delta M, delta Mi, that's delta M1, delta M, and so on. Okay, so with that, this would be the formula for the center of mass. The sum of all these delta Mi's will be the total mass. Okay, so the sum of the masses is the sum of the small mass is the total mass M. Let's call that mass to be M. Okay, so you've got delta M1 R1 plus delta M2 R2 plus delta M3 R3 and so on. Okay, well, let me write in a different way. Okay, we're going to divide this in small particles, but then we're going to push the size of these particles to 0. Okay, so we're going to say RCM is the limit of this summation delta Mi Ri divided by capital M as the delta Mi's approach to 0. Okay, and that is a definition of an integral. Okay, so you divide this in small particles and then you push the delta m to 0. Okay, that'll give you the center of mass of the solid. All right, but this is an integral, so with the following. So RCM is 1 over m, the integral of r dm. Okay, so we divide in small delta m i's and then we push the delta m to 0, we get an integral. Or we can say xcm equals 1 over m, the integral of x dm, or ycm equals 1 over m, the integral of y dm. Okay, so these are the formulas to be used when calculating the center of mass of a solid. All right, now let's consider some examples. Example, find the center of mass of a uniform rod of length is L. Okay, so let's say we have this rod. This length is L. So let's say I put my coordinate system over here. So this would be L over here. Okay. So to do the integral, we need to take an arbitrary point over here. Let's call this dx. Okay, and this would be x dx. Now let's look at the integral. This is one-dimensional case, so we just need the x. Okay, this is the formula. 1 over m, the integral of x dm. Okay, so we need to convert this to position integration. Let's say the mass of the rod is L. Now the way we do that is we can use the formula for density. You see it's uniform, so the density is a constant, right? So if you use lambda for the density, we have lambda equals dm by dx. The dm is the mass of this part of the rod. Okay, so that gives us dm equals lambda times dx. But lambda is uniform, so it's also equal to the total mass divided by the total length. We're talking about linear density. You see, you've got dm equals lambda times dx. Okay, so if you integrate this, you get total mass, and then if you integrate this, lambda is a constant, you get the integral of dxl. Okay, so lambda is total mass divided by the length. All right, so we can write as follows now: xm equals 1 over m, the integral of x dm. Dm is lambda dx, lambda is m over L times dx. Okay, and the value of x varies from 0 to L. Okay, so the integral goes from 0 to L. So this is the integral we have to do. All right, so we have xcm equals, you see this m will cancel this m, so we've got 1 over L, the integral from 0 to L of x dx. Okay, so we have 1 over L, and then this is x squared over 2 going from 0 to L. Okay, so that's 1 over L times L squared over 2, that's L over 2. So as expected, the location of the center of mass is as the geometric center because it's uniform. Okay, another example. Now find the center of mass of a uniform rectangular object, rectangular, let's say plate, of width is A and length B. Okay, assume the mass PM. We're not going, we don't need it back there. Mass to PM. Okay, so that's what we have over here. We have this rectangular object over here. Okay, let me put my coordinate system over here. So this is my Y, this is my X over here. So the width is A, so this is A, and the length is A, so this, I mean B, so this point over here will be B. Okay, so the question is to find the center of mass. It's uniform, so we know it's going to be this geometrical center. We're just trying to apply the formulas. All right, so first we're going to find XCM. Okay, so let's take this strip over here of size dx. Let's say this one is this size over here, dx. Okay, and then of course this is x over here. Okay, when you integrate, usually you need a representative element. All right, now it's uniform, so this is areal density. Areal density is usually denoted by sigma. So we get sigma equals dm by the area. You see the area of this strip is this width dx times its height b. So the area is b dx times dA, or dm is b times dx. Okay, so we have dm equals its density times b times dx. Okay, now this is uniform, so the density is total mass divided by the area of the plate. Okay, this is the density because it's uniform. All right, so you've got the following: dm, this is small, dm is the mass of this strip over here, is the mass of this strip. Okay, so we have dm equals m over ab times b times dx. Okay, b goes away, so we got m over a times dx. Okay, now let's go to the formula for XCM. This is 1 over m, the integral of x dm. Okay, now we're going to replace this for dm, so you've got 1 over m x, and then we've got m over a dx. Okay, and the value of a, I mean the value of x, you see this strip could be anywhere, it's just a representative element, so it's x goes from 0 to a. Okay, so this goes from 0 to a, so that's the integral we have to do. All right, so let's take the constant out. So you've got the m cancels out, you've got 1 over a, and the integral is x dx is x squared over 2. That goes from 0 to a. Okay, so that's 1 over a times a squared over 2, and as expected, the location of the center of mass is halfway along the x-axis. Okay, so halfway. So that is the value of the x-coordinate of the center of mass. We're doing the same thing for y. This is the x-coordinate of the center of mass. Now let's work on the y-coordinate center of mass. To do that, we're going to take another strip in this direction. That's going to be our mass element. Okay, and this is going to be our dy over here, okay, our maximum dy, and as you know, y is going to vary from 0 to b over here, okay. So what's the area of this strip over here is dy times a, okay. So once again, well, this formula is going to be like this: 1 over m, the integral of y dm, okay. So we have dm is, no, I mean the density. The density is dm divided by the area. Now the area of this strip is dy times a. You see, dy times a. So this is dy times a. But the density, we already know, it's mass over area over AB. Okay, so A goes away, so you get the following formula: dm equals m over b times dy. Okay, so we have ycm equals 1 over m, the integral of y, and dm is m over b dy, m over b dy, okay. And the integral is going to go from 0 to b, you see. This is y over here, y. So the value of y goes from 0 to b, alright. So we have, this goes from 0 to b, so that's the integral we have to do. So you see m goes away with m, so we've got, this is 1 over b, the integral from 0 to b of y dy, okay. That is 1 over b, and this is y squared over 2 going from 0 to b, and we get 1 over b, b squared over 2, that's b over 2. So ycm is also b over 2. All right, therefore the location of the center of mass, which is xcm, ycm, is a over 2 for x, and b over 2 for y, as expected, which is the geometrical center of the rectangle. Okay, now let's look at the dynamics of the center of mass. Dynamics of the center of mass. That is Newton's law applied to the center of mass. All right. Now, let's say you have a system involving a lot of particles over here. Okay. So what's the net force acting on this object? Okay, well, you know, Newton's second law says net force equals mass times acceleration, right? Okay, so we're trying to find the net force acting on these objects. So, well, we can add the net force on each particle, okay? So we can say the net force is the sum of the force on particle 1 plus the force on particle 2, and so on. This is the net force acting on the object. Okay, now I have to say that there could be forces between these particles. Okay, it could be electrical, any kind of force, but you see, those forces are actually reaction force, so the internal force do not contribute to the external force, because this particle exert force on this particle, that particle exert force in the opposite direction on that particle. Okay, so all the internal forces are going to cancel each other. So when we talk about net force, we're talking about external forces, that is forces exerted by particles outside of the system. Okay, so F net is equal to F external. This is force exerted by objects outside the system. So internal force do not contribute to the net force, because internal force, they're action-reaction forces and they cancel each other. Okay, so we can replace F net by external force to emphasize the fact that it doesn't include internal forces, because the sum of all internal forces is going to be zero. For each force, there's going to be a reaction force. If one particle exerts force on one particle, that particle is going to force in the opposite direction. And since we're treating the single system, then the sum of all the forces is going to be zero. Okay? All right, so we can replace this one with external force equals M1 A1 plus M2 M2 A2 and so on. Okay, but remember the definition of the acceleration of the center of mass? It was M1 A1 plus M2 A2 and so on, divided by the sum of the masses. Okay, now let the sum of the mass be M. Okay, M1 plus M2 and so on equal to M. So that tells us this M1 A1 plus M2 A2 and so on equals total mass times the acceleration of center of mass. Okay, so you see this expression over here is equal to this one. So you got the following formula. So the external force acting on a system is total mass times the acceleration of the center of mass. Okay, so when you deal with the dynamics of a system of particles, you can assume that the total mass is concentrated at the center of mass. So you can deal with it like the total mass of the particle is concentrated at the center of mass. So this means in applying dynamics to a system of particles, it can be dealt as if the total mass is concentrated at the center of mass. So the total mass is concentrated at the center of mass.